Yeah. Morning, folks. So, let's see. This is the last week on Lab 1, right? But most people have already finished Lab 1 and started Lab 2. So are there any questions about Lab 1 or Lab 2? Questions about Lab 1 would clearly be like write-up at this point. Yes? It is due the Thursday after the last scheduled day of the lab. The Lab 2 is pretty hard, so starting early is not a bad idea. Any questions on Lab 2? Last time I went through Lab 2, sort of logical setup and some of the some of the math, and it's really nice when people yell as they go up and down the halls, isn't it? Yeah, we could close the doors if we had to. If you get tired of listening to it, you can close the doors. So, any questions about the logical? The one question that was asked last time is, would I go over bus masters again and how to build a bus master, and I will. And I can also talk about p-threads at this point. It might be a good time to talk about p-threads a little bit, which is the standard, the POSIX threader, Linux threader. Anything else? Differential equations? How many people have gotten have run the MATLAB program? Oh, you got to start, guys. You're already late. Run it like today. Start getting your brain warmed up. So, where shall we start? More about bus masters? Yeah? Yeah. All right. Or do you want to go back and look at the Lab 2 write-up any at this point? No? Yes? If you have no opinion, it doesn't happen. So, bus masters. The goal here is to, again, the Avalon bus and the bridge over to the HPS is arranged as address generators and address consumers. The address generators, a device that can emit a bus address, is a bus master. And if it's responding to an address, it's a bus slave. And you need both. There's a number of bus slaves that are predefined that you can drag out onto QSys from the QSys module directory, including parallel ports and timers. So you wouldn't typically build your own timer. You'd just put a timer on the bus. You could even wire up an interrupt back to the HPS if you wanted to from a timer module. You can have as many timers as you want because you can just keep dragging them onto the QBus. I have not been brave enough yet, however, to insert an interrupt routine into the kernel. So you'd have to figure out how to do that. There's directions on how to do that online, but I haven't done that yet. But there's lots of bus slaves. What you don't see many of in the module list are bus masters, because it's assumed that either the HPS or, in the old days, the NIOS 2 would be the bus master that pulls all of the strings. But when you start building coprocessors that have to have some autonomous action, have to be able to do things on their own, then you need to write a master. So the bus master page has several examples going from kind of completely diddly to fairly complicated. I started out by doing simple stuff first because how else can you possibly figure it out? And so but the baseline was that there had to be a high performance system included, because everything is going to use some sort of user interface through the HPS, or is going to be using the Ethernet connection to send data across. And I left on LEDs, the hex display, slider switches, push buttons, and then my own external master. So this is kind of the baseline system, and this gave me the ability to have two kinds of input, buttons and switches, and two kinds of output, LEDs and hexadecimal display. So I figured I could at least figure out how the input-output worked from a bus master without getting into higher order stuff like video and audio. And because I wanted the external master to be able to control the two displays, then the Avalon master from the bus master is wired up to the hex display slave connection. So there's a connection from the Avalon master here up to S1 on the hex display, and to S1 on the LEDs. It does not, however, is not wired to the AXI slave. I didn't want the HPS to have anything to do with this. The push buttons and slider switches are wired to the lightweight master, because that was just the default. And but I removed the connection from the lightweight master to the LEDs in the hex display, because I wanted to make sure it was my master that was actually driving them. So it's kind of a minimum QSys setup. Oh, and the addresses are defined over here as usual. The LEDs were at 0, the hex displays are at 20, the switches are at 40, and the push buttons are at 60. And the external master does not have any address because it generates addresses. It doesn't use them. Any questions on this? My goal on all of these QSys layouts is the goal I have with every layout, graphic layout language. If you're going to do an example, you have to get it onto one screen so you can capture it. And so all of these are short enough that I can put them on one screen. That's the design max. So, do I need to go back through the EBAB documentation again? I'll go through just a little bit here. There's the EBAB mediates between the Avalon switch fabric and whatever you're writing over here. So this external master peripheral is your intellectual property. That's what you're going to be doing for this course. And your external master is going to need to generate addresses to write to, data, a read-write command, and these are mutually exclusive. I've never tried reading and writing at the same time. I think it's a bad idea. A byte enable signal, and then the sole feedback from the bus is the ACK. And of course the data that you may want to read. So this particular example, the HPS does very little. It's only hooked up to the switches and the keys. And so all I do is to go around, is just a loop that constantly asks for any input and then prints out the switches and the keys, except that if you hit X, the program exits. So that was because I got tired of hitting Control C. So it cut down the number of keystrokes by 1. So the HPS is really doing nothing here with the Busmaster. All of the interesting stuff is done by the top level module, and even that is not doing very much interesting. There's a hex decoder which is defined, which takes in hexadecimal numbers and puts out segment numbers that have to be lit, and they're active low, so you have to do some decoding. And at the bottom of this file is the decoder. But that's all of the Verilog that exists, except for the interface code that QSys generated. So the external master, when you export the controls from an external master, you get these 7 interfaces defined. And I forgot to point out on the QSys that I did export the Busmaster controls. And I just hardwired these to various pieces of the external FPGA circuitry. So the external master address lines, I'm setting off switches. And there's only 2 values that I care about because I only wired the Busmaster to 2 slaves. One had address 0, the LEDs, and the other had address 20. So I'm either going to flip on bit 5 or I'm going to flip it off, and that's it. I'm only writing 1 byte of data. I'm never reading, so I'm just latching that at 0. I'm using key 0 to actually cause the write command. That way I could tell when the LEDs changed, it was me that was doing it. You press it, the LEDs change. Switches 0 through 3 are the write data. So I'd set a switch pattern in there, hit the key, and it should be reflected onto the LEDs or the hex display. So it's completely manual, which is nice for testing, and it's slow. And there's only one shortcut here, which is terrible style, and that is I didn't bother to do a bus acknowledge. Why? Because my finger bandwidth is way, way slower than the bus. And I really doubted if I could do 2 writes in a row that were fast enough that an ACK was actually necessary. In real code, you always read the ACK, and all my other examples do that. And of course, since there was no data to read, I didn't bother to hook it up. So the entire interface to the Busmaster here is off the LEDs and switches on the board itself, with no input at all from the HPS. Any questions on this? So this is easy to set up. It's easy to play with. It exposes all of the essential pieces of the Busmaster except the ACK and read. But you're generating an address. You're setting you're setting an address, you're setting some data, you're hitting the write button. So we can now go a little bit more sophisticated. And in this example, which I did a fairly long time ago, I had not yet written the address.h file. So I hard-coded everything into the code. Don't do that. Use the address.h file. There, the LEPIO base from QSYS is at 0. The hex is at 10. I did include that. Wow, that's strange. Okay, I have no idea then. Do the usual. Oh, this is this piece. The HPS switch is on the HPS side, not the FPGA side. Don't use that. The rest of this generates the virtual to machine, virtual to real address translation, and then the little address decoder. The address generator is going to take one of 3 letters: an X, which kills the program, an H, which sets the bus master address to hexadecimal, or 0, which sets the bus master write address to 0. And the output from the HPS is going to be routed through a parallel I/O port separate from the bus master, which will control the bus master. And it says switch address. Oh God, I got so lazy. I just reused the switches as a write port, and reused it for addresses rather than renaming it. I'll probably live to regret that because of the number of questions it'll make. QSYS layout is just slightly different. Except so here the lightweight AXI master is wired to the external master address slave, because the HPS is going to write to the parallel I/O port. You could tell this is a parallel. This is my name. That's what it actually is a PIO. And then this is exported to a signal called slider switches, which again I'm repurposing as an address. The external master is still wired to the LEDs and the hex, and there's nothing on the QSYS side to suggest that the parallel I/O port controls the bus master. That is done in Verilog. So the bus interactions are done here. The HPS is controlling the address. The external master is controlling the LEDs, and the connection between here and here appears in Verilog. Question? Yeah.
Just go that one more time.
Sure. So there's a program running on the HPS that's going to output one of 2 numbers to the parallel port, either hex 20 or hex 0. And we're going to use that as the write address for the bus master. So since the HPS is writing to the parallel I/O port, the lightweight bus has to be able to talk to the parallel port slave. So this line goes up to the high performance system lightweight bus, and we're using the lightweight bus because you can sustain up to about 700,000 transactions a second on that bus, and that's fast enough for switches or for setting addresses. The external master is going to control the LEDs, and so it's wired to the LEDs. However, the connection, the way that the parallel I/O port is connected to the external master is through a connection in Verilog. So that'll be at the high level module rather than at the QSys level. Yes.
So this is just like an example to educate us in how to communicate, right?
This has no practical use.
Okay.
This is just setting up toy examples to figure out how in the hell to use a bus master.
Okay.
And so there were a few steps. First step was, can I use switches to change it? The second level was, how do I use the HPS to control a bus master? You're going to need to do this in lab 2, because you're going to wire parallel I/O ports to the HPS bus master. Those parallel I/O ports are going to set spring constants and start-stop conditions, which will then be wired through Verilog to the bus master, which is running your simulation and writing to the VGA.
So the parallel I/O is pretty much just like our catch-all bus slave for the FPGA.
Parallel I/O ports just I/O lines, right? That's its most useful thing you could have is more I/O lines. And so you can put as many of these things as you want on it, but they're quite non-specialized. In fact, most of the specialized modules that you see on the QSys layout for the standard university computer are just renamed parallel I/O ports.
So parallel I/O the external interface could be GPIO or LEDs or a wire in Verilog?
Yes, they're all options. You could take the parallel I/O port in QSys and export the connection to it. Let me go back. So for instance, the LEDs are actually a parallel I/O port whose external connection is exported to a Verilog variable, a Verilog signal LEDs. That's available in the top level module when you get around to looking at that. You could take this signal and route it to the expansion pins. Just take it out the expansion pins. Then you have actual off FPGA I/O, up to 72 lines of parallel I/O. It's really fast too. If you double click this name or this name, you'll get a dialog box that opens up that says, do you want I/O or you want input or output for each pin? You get to choose which pins are input and output. And of the up to 32 bits pins per I/O port. And I think that's the only options. There's no pull-ups, except on the I/O pins. There's pull-ups and tri-states. So these exposed wires in Verilog can be anything you want. So it's general parallel I/O. Did I answer what you were asking?
So if one of those connections, the external connections, is set as an input, this PIO module is an Avalon slave. So it won't notify you of that?
No,
change?
it won't notify you of that change unless you turn on an interrupt.
Can you query?
You absolutely, you can query the slave for its input status, yes. So if you do a read, if you do a write to the slave address, it writes the LEDs. If you do a read, it reads the last value.
So you say you could do a parallel I/O that bypasses the FPGA. So you hook the Avalon map slave up to the HPS, and you map the external connection to say like the GPIO.
It doesn't bypass the FPGA. It goes through the connection fabric to the GPIO pins, because they're one of 650 I/O pins, and you're using the FPGA switch fabric to take the output of the module and connect it to the GPIO pins.
Okay.
So yes,
And that is achieved here.
that is achieved in Verilog. So at the Verilog level, you can hook anything to a GPIO pin, and I do that a lot for debugging. Is clock 27 running? Well, hook it to the oscilloscope. That's the only way to find out. Is the vertical sync running on the video input? So I commonly have 2 or 4 signals hooked to GPIO pins for debugging, any 2 of which I can look at with the oscilloscope.
Sorry, I'm asking a little.
Go right ahead.
So the LEDs are a wire in Verilog. All these things are a wire in Verilog. Why do we have to go through QSys to get there from the FPGA?
QSys is a way of organizing communication in the FPGA. It is not different than the FPGA. It's using something like 25% of the FPGA to build this bus.
Okay.
It is only that the QSys formulation here exposes some signals to be connected graphically, but not all of them. Things that are disorganized or custom connections or require external connection from the FPGA to the outside world are represented by this catch-all external connection conduit, and then you have to give it a name over here, and it appears in the Verilog.
Okay.
But this is all, you can export all of these signals and not wire up anything here and wire it all in Verilog if you want. It would be a twisted thing to do and probably confusing as hell, but you could do it.
Okay.
So now we go to the top level module where all these are exposed. We have the usual pile of I/O pins. I was driving the hex as usual. And then there's the bus controller, the bus master state variables. And what I'm doing here is counting slowly. And this was, I wanted to count at a lower than 1 per second rate so I could validate that counts were occurring when I thought they should be. And I could, when it was slow enough that I could flip a switch in between counts and figure out what was happening. So there's a little state machine here that is running a timer, slow timer. And the bus read and write has to be reset at key equals 0. And otherwise, the timer is running at full 50 megahertz on 25 bits. 25 bits overflows every, I think, 0.7 seconds or so. Then the main state machine for writing, you're sitting here saying, if the state is 0 and timer is 0, in other words, it just overflowed. If the timer just overflowed, then we're going to increment the slow timer. This is the one that's running at 1 tick per 0.7 seconds. So we're incrementing a slow timer. We set up the bus write data to be the slow timer. So it's being spit out to the data bus so we can look at it on the LEDs or the hex display. We're going to send out 2 bytes, so we need to do the byte enable as binary 0011. And then we're going to input the bus address input from the parallel port. I haven't looked at that yet. It's down a little bit lower in the code. So this is going to come from the parallel I/O module. Then we set the bus write parameter to 1. We wait until the state is 1 and the bus ACK is 1, and we set everything back to 0. So this is doing the state machine for writing, the full state machine for writing, which has a setup and an ACK state always together. So all we need now is the connection to these modules. So once again, we have the external master interface going to these completely opaque and useless. Bus address goes to bus address, enable goes to enable. Okay. So these are all being set in the state machine that we just looked at. And the only thing that's left dangling here and we have to look at is, wait a minute, where did that, oh, the slider switch export I reused again. Again, I'm gonna hate myself for this. I used the slider switch export and named it bus address input. Because since it's an I/O port, it was originally named to be an input, but I'm using it as an output. So the output from this port, this is the export from that parallel I/O module. This is that's what it was exported from the parallel I/O module. It becomes the address that was entered at the keyboard in the HPS program, because the HPS busmaster is driving the parallel I/O port. There's lots of levels of abstraction here. There's the C program running, which is messing with I/O addresses. The I/O addresses then map to become data in a parallel I/O port, which is exposed to become an address in the state machine. So 3 parts, the C program, the QSys layout, the Verilog, all have to be consistent and work together to have the HPS control the busmaster. And that is this is the central piece of Lab 2. You're going to write a serial command parser, a serial terminal command parser, that is going to ask for, in some reasonable way, for floating values of spring constants and start-stop commands. That is then going to communicate those values over to a series of parallel I/O ports, or maybe one parallel I/O port if it's really wide. After you convert those values into fixed point, because you don't want to do that on the FPGA side, you really, really don't. You want to do that conversion from floating point to fixed point on the C side. When you hit the start command, your simulator is going to load the initial conditions, and then do the dynamics, and the dynamics are going to move, and the simulated masses are going to bounce around. You're going to output the bus master, then will manipulate the VGA interface to write onto the screen until you ask it to stop by way of the HPS. To do that, then, the parallel I/O ports you use are going to have to be, the bus slaves for the parallel I/O ports are going to have to be mapped onto the lightweight bus of the HPS. The bus master you write is going to have to include the state machine that runs your simulator, plus the state machine that writes VGA points. So it's going to have two parts. So the bus master module, so you have the Avalon bus here. You have the EBAB, the Avalon bus master, and then your bus master is going to take input from a parallel port or more, parallel ports. It's going to generate a VGA address. Let me make that a little bit bigger. VGA address. It's going to generate, for that VGA address, a color. And there's going to be two separate state machines running here. There's going to be state machine 1, which is the simulator. And there's going to be state machine 2, which is the bus write machine. So every so often in the simulator, the bus write machine is going to say, I need those 2 points, grab the values from the simulator for x1 and x2, and write them onto the VGA. How often? Maybe every 50 points, 50 simulation points to start with. Maybe, let's call it every 2 to the 5th simulation points. What?
What does that say? E something?
Avalon.
Did you write about?
EBAB.
What does it stand for?
External bus Avalon.
That's what I've been talking about. That's the bus master. Okay, so you're going to generate a QSys layout. When you generate the QSys, it'll produce a top-level module. You will copy that module interface into your project space and instantiate it. So the instantiation here is where you do the connections. Instantiating it, the name of the module type is computer system, and the instantiation is the system. That connects the QSys modulated interface to your Verilog code. So this whole module, all of this mess, all of the DDRAM, the HPS I/O, GPIO, all has to be there. If you start commenting out some of these command lines on the HPS side, interesting things will happen, like the Ethernet won't work. But in particular, you're going to have at least 2 or 3 or 4 exported control sets for parallel I/O ports, and you're going to have at least probably one bus master with these signals that you're going to then connect to your state machine 2 over here to do the writing, while state machine 1 is running the simulation. State machine 1, you are going to completely simulate before you ever put it on the FPGA. It is independent of all of the bus interactions and all of the hardware. It is just math. Therefore, it's easy to simulate. And logically the most difficult. Nice combination. Questions?
There's something I don't understand from the earlier questions. So if we wanted to connect the GPIO ports to the HPS, that's done through the FPGA fabric, correct? And that's configured in Verilog.
Mm-hmm.
It seems reasonable that QSys would give you that ability. Is all
Yes, I mean, why isn't there a GPIO module, right? And that seems like a reasonable thing to do because it's more I/O. Let me show you an example of how I did it here. Going back now to the university program, there's a new little piece on this, and this is not a stereo image of me trying to figure out how in the heck the camera works. But the top level module, by way of debugging this, the first thing that's in the top level module is to take the signals that are well, this was supposed to be set up by the video in intellectual property from Altera, but it in fact does not work. And then these are all inputs from outside the FPGA. So these are all inputs from an external codec, which is external hardware from the FPGA. And you just map them to I/O pins. You could write a module that does this.
It seems to be their convention that anything that has to do with pin assignments is done in Verilog, that you export from QSys to Verilog.
That's true. And one reason is that any connection external to the FPGA must occur at the top level module. So these connections have to explicitly be in the top level module. So if you were to write it in the system, you would have to generate a script which would generate the top level connections in that module. Yeah, so the way I got around this TD reset not being generated by the IP was, if you look at the top line up there, I just hooked it to switch 1 so I can hit reset by toggling switch 1. It's really crude. It works. The side effect of this is when you turn off switch 1, it halts the video input, and so you get a still frame capture. So it's not a bug, it's a feature. But I could take any one of these some of these are mapped directly. Is there a that's right. In the original computer, in the original university computer, there's two ports called expansion JP1 and expansion JP2. And And the original code that came with it, the high level, the interface module maps those directly to the GPIO pin. So this shows you how to do it. Why is GPIO 1 there and then it goes, why is 2 skipped? It's VDD. I would not have laid it out that way, but never mind.
So that's section not on top of a module?
This, by putting that here, it assigns the, let's see, this is actually split across a line because of the narrow screen here. So the output port name is expansion JPL export, and then this is really part of the same line, which is the external signal at the top level. So all the time you're designing this, you're going to have to keep 3 different levels of abstraction in mind at the same time that have to be consistent. The C program generating the commands, the QSys, which generates the bus connections to all of the modules, and the Verilog, which is going to make the detailed connections between the modules. That's why I suggested the testing strategy that I did, because if you go with the testing strategy here, as you step from 1 for simulation to 2, which is model sim, to 3, hard coding the constants, to 4 with the hard coded with the plus HPS, at least you'll be able to see output at every stage. And that's reassuring, because then you can incrementally correct it if you can see something. If you see nothing, yeah, you may as well figure out how you're going to break the system down. Okay, I can do more Busmaster stuff next time. I've written now video and audio Busmasters. I can talk about the video input such as it is. Talk about maybe I'll talk about p-threads next a little bit, and then go back to Busmasters. How's that sound? Any last questions? Given week, I can be in lab on Wednesday afternoon if it's helpful. If you want office hours on Wednesday afternoon from 1 to 4 or any of that time, I can do that. Email me if you think that's a good idea.